So I volunteered to introduce Marta just because I know her a little bit. So the short story is that I met Marta maybe 2 or 3 years ago, and I was in Spain at some meeting, and Natalia Cavo is a faculty member at this university, Universidad Complutense de Madrid.
Yeah.
And so I went there to give a talk and visit the students there. And Marta came up afterwards and introduced herself, and we had some common interests. She organized actually a visit to come to NCAR under some Spanish funding. So she came, we had been exchanging emails, and she kind of said, I'd like to come visit. So she came to visit for a while. This is a couple of years ago, or a year and a half ago. And she came over, and it turns out we have a lot of things in common interest. And so she stayed, and this is her 3rd visit now to NCAR. And she's finishing up her PhD sometime relatively soon. She's actually living in Paris now, but yeah, living in Boulder right now. So that's about all I have to say. But Marta is one of the few graduate students. Actually, I suggested that she give a seminar. So it's kind of unusual to have a graduate student give a seminar. But I know she's done some good work there. So I suggested this, and Marta first didn't think it was a good idea, but then she thought about it a little bit more, and she thought it was a good idea. So welcome.
All right, thank you very much. Does this work? Yeah. Okay, so thank you very much for coming, everyone. So as Bill said, I'm going to present the main results from my PhD that I will defend in a few months. And I've been so I'm doing this work with Encarna Serrano from Universidad Complutense Madrid. He's my advisor back in Spain, and here working with Bill. And we're trying to understand the variability in upwelling near the tropical tropopause and how it affects tracer transport. And I want to say thank you to ACD in general for hosting me in all these visits and making me feel very welcome. It has been really nice. And then also in particular say thank you to Doug Kinnison, Mijon Park, and Fei Wu for providing and helping with the data, both model and observational data. Okay, so this is the outline of the talk, and I'll first give some background and motivation for this work, and then I'll show the results for the variability in upwelling and how it's linked to the temperature and tracers in the tropical lower stratosphere. And I'll focus mostly on the annual cycle, but I'll also show some results for subseasonal variability. And the results that I'm going to show are based both on observations and on a simulation with WACCM. And then I have just a couple of slides to show the most recent work that we're doing now, where we're looking at the drivers of subseasonal variability in upwelling. And then I'll summarize the main results in the end. Okay, so I wanted to start by showing this schematic of the global zonal mean circulation of the stratosphere, which is called the Brewer-Dobson circulation. And so by looking at observations of water vapor in the stratosphere, Brewer and Dobson realized that in order to explain the very low concentrations of water in the stratosphere, the air masses must have traveled through regions of very cold temperatures, such as the tropical tropopause. And also, they observed very high concentrations of ozone here in the lower polar stratosphere, and this could only be explained if the ozone was being transported from the tropical stratosphere, where it is mainly produced by photochemistry, towards the extratropics and downward. So they proposed the existence of the hemispheric mass circulation in the stratosphere, which with upwelling in the tropics and polar transport and downward transport over the high latitudes. And this mass circulation has actually been confirmed later to exist by some diabatic calculations, and also as more and more observations of tracers have become available of the stratosphere. And the white arrows in this schematic indicate the current picture of the Brewer-Dobson circulation. And you can see that in this schematic, as well as this mean advective transport, there's another kind of transport mechanism that is very important in the stratosphere, and it's shown by these wavy orange arrows. And these show two-way eddy transport and mixing in the stratosphere, which is mostly important, as you can see, in the middle latitudes in the stratosphere. So just by looking at this general picture of transport, you can see that the region near the tropical tropopause is particularly interesting because it's where most of the air masses enter the stratosphere, and so that the variability in upwelling across this region can have a large impact on the chemical constituents, the concentration of chemicals in the stratosphere. However, the magnitude of this upwelling is very small. The ascent is lower than 1 millimeter per second, so that it cannot be directly measured, and we need to estimate it indirectly. And in this region also, several tracers present very sharp changes in their concentrations from the troposphere to the stratosphere. And this is the case, for example, for ozone or water vapor, carbon monoxide, and other tracers. So this figure shows the mean ozone concentrations for boreal winter from satellite observations. So this is cross-section, latitude versus height. And I just want you to focus on this part where you can see that the isolines are all stretched together, indicating very strong vertical gradients in ozone in this region where upwelling is happening. So that even small variations in the intensity of the weak upwelling can have an enhanced effect on the concentrations in this region above the tropical tropopause. So in this context, the general questions that we addressed in the study are: how well do we understand the variability in upwelling in this region, and what drives this variability? And then how important is upwelling for the variability in temperature and tracers in the tropical lower stratosphere? So one thing that is well known about upwelling is that it has a large annual cycle, and it shows, so the vertical velocities in boreal winter are twice as fast as in summer. And so this annual cycle in upwelling has been shown to be linked to the large seasonality in temperature that is observed just above the tropical tropopause. This figure shows the annual cycle amplitude in tropical mean temperature as a function of height. And you can see that in the tropical troposphere, there is very little seasonality or no seasonality. But as we go across the tropical tropopause, we see a rapid increase in the annual cycle amplitude of temperature. And there is a sharp peak just above the tropical tropopause. So we have these very large annual cycles over a narrow layer above the tropical tropopause. And this figure shows the seasonality in temperature at the level of the maximum amplitude. And it's shown here, and it's shown together with two estimates of tropical upwelling. And so you can see that a stronger upwelling in boreal winter is bringing cold air masses from the cold point tropopause below to this level, so that we have colder temperatures in winter as compared to summer. And in this figure, overlaid with temperature, you can also see an annual cycle in ozone, which is almost in phase with temperature. And so the question is, what drives this annual cycle in ozone? And in this paper by Rando et al. 2007, they addressed this question, and these are figures from that paper. And the left panel shows the annual cycle amplitude in ozone as a function of altitude. So you can see that the vertical structure is actually very similar to what we saw for the temperature. This is shown for different observations, and there is more noise in the troposphere among different values among different stations in the tropics. But you can see that this big peak above the tropical tropopause is seen in all the observations. And on the right panel, you see the vertical structure of the relative ozone vertical gradient. You see that the gradient peaks has a sharp peak at approximately the same level where the maximum amplitude in ozone is found. So these coherent vertical structures suggest that the large annual cycle in ozone is mainly driven by the seasonality in upwelling, acting on these large background gradients in ozone. But then more recently, there have been a number of studies from a group in Jülich in the research center in Germany, where they used a Lagrangian transport model, and they obtained a very large annual cycle in mean mixing, which is horizontal transport of ozone from the extratropics into the tropics. And in particular, they observed very large in-mixing rates in boreal summer, and they were associated with transport from the Asian monsoon. And so the Asian monsoon anticyclone is a dominant feature of the summer circulation, boreal summer circulation, and there is a lot of interest in understanding what effects it has on the concentration of different tracers in the upper troposphere and lower stratosphere. And as you can see here, what this circulation does is it takes the air masses from the extratropics, which have very high ozone concentrations, and transport them towards the tropics. So in these works, it was shown that if they got rid of in-mixing in the Lagrangian model, then the annual cycle in ozone basically disappeared. So this suggested that horizontal transport and not tropical upwelling was the main driver of the seasonality in ozone in this region. So actually 2.5 years ago, I came here for the first time, and we started working in this observational study, which is now in ACP, and where we looked at the variability in upwelling from observations and how it was linked to tracer variability. So we used satellite observations of ozone and CO from the MLS satellite instrument, and we combined that with ERA intermeteorology. And for upwelling, we computed 3 different estimates, independent estimates. Okay, so this is a key figure, motivational figure for that paper, and it shows a time series of observations of temperature and tracers at 3 pressure levels across the tropical tropopause. So, well, all the series are standardized, and carbon monoxide is inverted to show to match the variability of temperature and ozone. And so what you can see here is that there is a high degree of common variability between the temperature and the tracers in this region. And this is especially evident in the large annual cycles that are seen in all the variables. But also, if you look at subseasonal fluctuations, you can see that very often there are also common fluctuations on these smaller timescales. So the question that we address here is what drives this common variability between the temperature and tracers. And as I said before, we computed 3 different estimates of upwelling, and we did this to compare them and have an idea of the degree of agreement that we have for upwelling. So the first one is just the residual circulation. So it basically depends very strongly on the vertical velocity from the reanalysis, and this is usually, well, this is not constrained, of course, by observations, and so it has large uncertainties. And the second estimate is computed from momentum balance, and it depends on how good are the dynamics in the reanalysis, because it's computed from eddy, fluxes of momentum and heat. So, and since not all the waves are resolved in the reanalysis, then there are also uncertainties in this estimate. And finally, the third estimate is computed from thermodynamic balance. And here the key magnitude is the heating rates, which we computed from an accurate radiative transfer code. And okay, so these are the results. And so these are the time series, daily time series of the 3 estimates of upwelling at the same 3 pressure levels across the tropopause. And on the right, you can see the mean annual cycles for the 6 years period. And so as you can see, the 3 estimates don't give the same value of upwelling for every day. And in particular, if you look at this lower level, the green curve is the vertical velocity from the reanalysis. And it is known that ERA interim overestimates the vertical velocity in about 40% near the tropopause. But if you look overall, the 3 upwelling estimates have a reasonable agreement in the mean values and the overall seasonal cycles, and also on subseasonal, for subseasonal fluctuations. So we, and the linear correlations are around 0.7. So, which is actually encouraging, because we have all these uncertainties into each of the estimates, and they're computed from very different, in very different ways. So we like these estimates, and we use them to investigate the variability in temperature and tracers. And I will start by showing the results for the annual cycle, and these are the results for temperature. So this shows the mean seasonality of all the terms in the thermodynamic equation. And this equation gives the temperature tendency as a function of many terms. And so this is the horizontal advection, vertical advection by tropical upwelling, heating rates, an eddy term, and then we have a residual, which we need to include to account for the uncertainties in all the other terms and possible imbalances. So you can see that the overall budget is that for the annual mean, there is an adiabatic cooling by tropical upwelling, which is balanced in the annual mean by the diabatic heating response of the atmosphere. And you can also see a large annual cycle in the upwelling term, which is mirrored in the temperature tendency. And the large response in temperature in this region is, well, the response in temperature is particularly large in this region because due to the long radiative relaxational timescales here. So this is the balance for ozone now. Now this shows the seasonal mean of all the terms in the ozone continuity equation. So now we have the ozone tendency, which shows a large annual cycle, as you can see, and it closely follows the seasonality in tropical upwelling. And in the annual mean, the decrease in ozone by tropical upwelling is balanced by the sum of these two terms, chemical production plus a residual. So as you can see, we have a large residual in this balance. And this residual accounts for the uncertainties in all the terms, but also it includes the eddy transport term, which we cannot explicitly compute from the observations. So we think this residual is mainly due to this eddy transport term that we don't resolve. And this is the balance for carbon monoxide, and now you can see the tendency of CO, which is somewhat more noisy than that of ozone. But you can still see the large seasonality, which is following the large seasonality in upwelling. So that stronger upwelling in boreal winter brings high CO from concentrations from below. And in this case, the residual is a smaller term, and the overall balance is between increase by upwelling and decrease by chemical loss. Okay. So we have seen from the detailed analysis of the budgets from the observations that upwelling acting on these large background gradients is the main driver of the seasonality in temperature, ozone, and CO. But we have this caveat of very large residual in ozone, in the ozone balance. And we think it's mainly due to this unresolved eddy transport, but we don't know for sure. So the good news is that there is a very nice group at NCAR which are develop and improve all the time WACCM, which is the whole atmosphere community climate model. And this is a chemistry climate model, and it has been shown to provide a very accurate representation of the dynamics and chemistry of the stratosphere. So we thought it was a good idea to evaluate these balances in the model and see where we could explicitly resolve all the transport terms and see how were these balances. So that Kinison provided 6 years of data from a free-running simulation with WACCM4. And so the first thing we needed to do is to see how WACCM performed in this region near the tropical tropopause, and which is a particularly challenging region for a model because due to these sharp changes occurring in very narrow layers. And okay, so this is the time mean vertical structure of temperature and tracers for the model and compared to the observations. So the model is shown in black and the observations in red, and there are GPS temperatures and some ozone zones, long record ozone zones for ozone, and satellite data for both tracers. So you can see that overall the model does a very good job in capturing the vertical structure, but there is a slight the cold point tropopause is slightly higher in the model as compared to the observations, and it's about 1 kilometer higher. And this could be just due to the limited vertical resolution of the model. Okay, so this is the vertical structure of the annual cycle amplitude in temperature and the tracers, and you can see that the model is able to capture this narrow vertical structure in the amplitude of temperature and tracers, and it captures overall the maximum amplitude and also the thickness of this layer of large annual cycles. But there is clearly a vertical shift in the level where the model is. Yes? Sorry. Mm-hmm. No, I just took the mean. So these are the mean. These are the same results used in the Rander et al. 2007 paper. So it's the mean of all the stations, annual mean. So I didn't compare each profile. It's the annual mean. Yeah, yeah. Yeah, maybe. I think, maybe there are more. This, for WACCM, this is a mean from 20 south to 20 north. And the ozone zones, I think, maybe are closer to the equator. But yeah, to do this global time mean comparison, I think you can see that they agree pretty well. And so, yeah, so there is this vertical shift in the level where WACCM presents the maximum amplitude in the cycles. So to take this difference into account, we evaluated the budgets at slightly higher levels in WACCM than we did in the observations to make sure that we were comparing levels that are equivalent in terms of temperature and tracers variability. So this figure shows the same time series I showed you for the observations, but now for the model. And you can see that I'm showing slightly higher levels. And now, actually, in WACCM, this is the level where the cold point, annual mean cold point, is located. So overall, you can see that the model does a very good job in capturing this common variability between the temperature and tracers. That is what we're interested in. So we think the model is a very useful tool for this analysis, and it's actually a powerful tool as well. So now we take the model results and we can compute explicitly all the transport terms. And these transport terms include mean advection by the Brewer-Dobson circulation plus eddy transport. And this figure shows a lot of things that I'm not going to explain, but I just want you to look at the colors. And the color scale is showing ozone tendency due to each of these transport terms. So the first thing you can see is that both terms are important make an important contribution for ozone tendency in the tropical lower stratosphere. And what you see in the upper panel is that tropical upwelling, vertical advection by tropical upwelling, leads to a decrease in ozone above the tropical tropopause, while the eddy transport occurs mainly along the isotropes, and so it's quasi-horizontal, and it leads to an increase in ozone. So this is the balance now for ozone in the model. So for simplicity, we group the transport terms in horizontal and vertical components of transport. And as we saw in the previous slide, the vertical component is mainly due to vertical advection by upwelling. The horizontal component is mainly the eddy transport. So the first thing you need to note here is that we have a small residual now. So we are able to close the balance in WACCM. And then you can see that overall the balance is very similar to what we had for the observations, with a large annual cycle in the ozone tendency closely following the large seasonality in the upwelling. And now in the annual mean, the decrease in ozone by upwelling is balanced by chemical production plus horizontal eddy transport. So So this balance from the model tells us that the residual that we got for the observations is actually can actually be explained by this horizontal eddy transport that we were not able to resolve in the observations. And now this is the balance for CO, and it's very similar to the observations as well. We have the large seasonality in CO following upwelling, and in this case the horizontal transport is smaller, so it's less important than for ozone, so that in the annual mean the increase by upwelling is balanced by the chemical loss for CO. And okay, now if we compare the balance at this level that we were seeing, a level in the lower stratosphere, with the same balance but at the tropopause level, you can see that there is a change in the seasonality of the transport term. And in particular, this large annual cycle in the upwelling term is not observed anymore near the tropopause, and it's a pretty flat term. So, and for horizontal transport, we have a clear peak for boreal summer. And this peak, this summer peak, is associated with eddy transport from the Asian monsoon. And to look at this change in the seasonality with height in more detail, we can look at this latitude versus month cross sections, which show the ozone tendency due to isentropic transport. And they are shown at these two levels that I was showing before. So in the lower stratosphere, there is an increase in ozone due to isentropic transport during winter and spring on each hemisphere. And this is due to transient Rossby waves that are breaking in the subtropics near the critical lines. But if we go to the tropopause level, we don't see this feature anymore. And instead, we see this clear maximum in boreal summer, which is associated to the Asian monsoon circulation. So just to summarize the model results for the ozone seasonality, this figure shows the relative amplitude of the annual cycle of all the terms in the ozone balance. So as a function of height. So you can see that here in the lower stratosphere, upwelling is making the largest contribution to the annual cycle in ozone, while the horizontal transport, so in mixing, makes an important contribution to the seasonality at the tropopause level, which is this Asian monsoon transport. Okay. So that was for the annual cycles, and now going back to these, our beautiful time series of upwelling, we can see that as well as the large annual cycles, there is also substantial variability on shorter time scales. And we want to understand if, we want to know how much we can trust these fluctuations and what impact do they have on the tracers. So what we did is take this time series and get rid of the annual cycle and all the longer time scales with the spectral filter, and then we get this time series here in the bottom. So these are the three estimates of upwelling, only fast fluctuations. And on the upper part, you can see the temperature and tracers tendencies at the same level filtered in the same way. So what you see here is that often the fluctuations that you observed that we observed in upwelling are also found in the tendencies, in the tracer tendencies. And the linear correlations between the upwelling estimates and the tracer tendencies are shown here. And as a function of, so for different pressure levels, function of height. And I just want to point out here that these common fluctuations that we observed in the time series are actually statistically significant. And they are larger at the levels where the vertical gradients are strongest in the tracer. And these are, this is a similar plot for WACCM. And so it shows a correlation for subseasonal fluctuations of temperature, ozone, and CO tendencies with the two main transport terms. And so what you can see is that upwelling makes the main contribution to subseasonal variability in the tracers, but there is also a contribution from horizontal eddy transport, and especially at the lower levels. So, okay, so then both observations and the models show that the subseasonal fluctuations in temperature and tracers follow the variability in upwelling on subseasonal timescales, and And the fact that we observe this common variability between the upwelling and the completely independent tracer observations from satellite gives us confidence on these fluctuations in the upwelling. So we use these estimates of upwelling to address the question of what drives the subseasonal variability in upwelling. And so I didn't want to spend a lot of time on this last part, but so I'm not going to tell all the results, but I wanted to give just a few highlights on what type of analysis we're doing. So what we did is take the time series of upwelling, in particular the momentum balance estimate, and we extended them to the full era interim record, and we only looked at the subseasonal fluctuations. So we removed all the annual cycles and longer variability, and we selected the cases with very strong upwelling. So we took the days with strongest upwelling in this time series, and this figure shows a composite of the EP flux for these days of strongest upwelling. So what you can see is that when upwelling is when there is large upwelling in the tropics, there is enhanced propagation of planetary waves into the winter. This is winter, sorry, northern winter stratosphere, and so we know that when these waves propagate, into the stratosphere, they will eventually break, and they will transfer westward momentum to the mean flow, and this by Coriolis, this will induce poleward transport, and continuity will require vertical transport, and this will result in a change in temperature, which in turn affects the zonal mean winds. So the point is that the wave drag in the extratropical stratosphere affects the global circulation, affects globally the structure of the atmosphere. So to understand how this wave drag is affecting upwelling in the tropics, we did some one-point correlations of the wave drag here with different fields. And okay, so this first figure is showing the one-point correlations of the wave drag, where the point is with the wave drag everywhere else. And the arrows are the correlations with the EP fluxes. So you can see, so this figure, what it's telling us is the spatial extent of the forcing. And we know that in order to affect the variability in upwelling, the forcing needs to reach low latitudes. It needs to get close to the boundaries of the tropical region. And as you can see here, this wave drag does not reach those low latitudes.
Is that true? I mean, you are looking at a fairly highly transient situation.
Yeah.
So the downward control idea doesn't necessarily hold. I mean, you can have transient circulations that reach into the opposite hemisphere, even if the forcing is not at the edge of the tropical region. In this case.
Yeah, so that's exactly what I'm going to show. So, good question. Yeah, so it doesn't reach, but now this is showing the response in the zonal mean wind to this wave drag in the extratropics. And so you can see that as well as this local deceleration of the flow due to the wave drag directly, there is a remote response in the wind. And in particular, you can see this acceleration of the wind that is happening just on the equatorward side of the forcing. And so what actually matters for upwelling is the net forcing, which includes the wave drag plus the response in the zonal mean wind. So this figure shows the net forcing associated with the wave drag in that location. And you can see that the net forcing, unlike the wave drag itself alone, the net forcing does reach this low latitude. So the message is that the response, this transient remote response in the zonal wind, is actually playing an important role on the subseasonal variability of upwelling. Does that make sense? Okay, so that's all I wanted to say. And just to summarize, we have seen from both observations and from WACCM that upwelling is mainly driven, that well, it mainly drives temperature and tracer seasonality in the tropical lower stratosphere. And then with WACCM, we are able to compute all the transport terms, and we have seen that horizontal eddy transport is actually an important term in the ozone budget. And we've seen the effect of this large effect of the Asian monsoon near the tropopause. And then we have also seen that subseasonal variability in the tracers is mainly linked to upwelling, but there is also an important contribution from eddy transport. And finally, that the zonal wind transient response to an extratropical wave drag plays an important role for subseasonal variability in upwelling. That's all. Thank you very much.
So we're webcasting, so if there are any questions, we can use the microphone.
So at the lower levels, or maybe even at, I guess, at 100 millibars, have you looked for, or do you see any correlations with convective activity, maybe particularly in CO?
Yeah, well, we haven't looked at that particularly, but you can see in CO, in the CO, so this is CO on an inverted scale. So this is low CO and high CO. And you can see this double peak in CO, which is linked to convective activity lifting the biomass burning emissions. So yeah, so you do see that, but
Okay.
we haven't looked much closer at convection.
More questions?
No, I just have a quick one. You showed that the horizontal eddy transport term is important for ozone, but not so much for CO. You give us an idea of why that should be so?
So the horizontal gradients in ozone are larger than for CO. So this might be one reason. Okay.
So following on to our discussions at lunch today, and I was sitting here kibitzing with Rolando, can you show us the results I think you have for the high resolution version of WACCM and looking at this bias near the tropopause? I think you have that slide. High vertical resolution.
Yeah. So.
Yeah, this is it. Yeah.
So this is a WACCM run with very high vertical resolution, like 200 meters or something like that, but it's with an older version of WACCM. But so he met my advisor from Spain, and he made this data available. So I looked at this comparison, and now you can see that when you increase the vertical resolution, you actually get the cold point at the, or at least the annual mean cold point at the right place. And also the largest seasonal cycle in ozone seems to get to the right place as well. So.
Okay, I have another question before you take that away. You said that this run had 200-meter vertical resolution?
I'm not sure. I didn't. I said
300 meters, so that's about 3 times the current vertical resolution. So you haven't done anything intermediate between those two. I'm hoping we can get away with, half the vertical resolution we have now. So, I mean, maybe worthwhile to try that. I don't know, when are you leaving?
This Sunday.
Okay, so that won't get done by you, but I think this is something that we really need to look at. Yeah, that's an impressive improvement, really.
It is, I agree.
So, yeah.
Also interesting that the temperature amplitude in WACCM is just a little bit larger than the observations.
Yeah. And this is the
amplitude of the annual cycle. But if she showed the mean, you can tell that the horizontal lines there are the tropopause, so they line up much better here.
Yeah, this is the cold point tropopause in both, so they're really close. Eric.
Any other questions?
So yeah, this is interesting with the the change in the vertical levels, because you know what you showed with the other run is that the horizontal seasonal cycle dominates essentially at the lower levels, like more in the observational study was different, but anyway, you know, you show that the vertical seasonal cycle is dominant, but it almost seems like the shift makes that so, you know, just above where the horizontal cycle is dominant for the annual cycle, and then so that,
Yeah,
you know,
so
if you
I
did that
think-
analysis for the high resolution run, would it shift down that upwelling and they'd be competing more
I
equally?
think everything would be shifted down.
But would the horizontal inmixing be shifted down as well? Would it, or would it stay
because
there?
the tropopause will be shifted. I think but I don't know.
Yeah.
It would be nice to do.
Because that's
but-
interesting. I don't know whether the monsoon, you know, influx would be shifted down. My impression is it wouldn't necessarily. So then the horizontal inmixing would come in to play a little more equally, maybe. Not sure.
So I think this is something you won't know until you try it. I mean, if the waves doing the mixing are the same ones as the ones driving the seasonal cycle, then everything should shift down. But maybe that's not the case. And the waves are responsible for the mixing, say maybe synoptic waves, whereas the seasonal cycle may be driven by you know, quasi-stationary tropical Rossby waves. And then you may have a different apportionment of mixing and upwelling. But until you try, you won't know.